All right, well, thank you for being here. Before we begin, I just want to acknowledge the first author here, Russell Collins. He wasn't able to make it to Philadelphia, but he did do a lot of the work. So discrepancy in prescriptive shear reinforcement values that we use for slender and non-slender beams. So I'll talk about the motivation for this study, go into background methods used and results, finally the conclusions. If you want to find out more details, you can find them here in this source. So the minimum reinforcement requirement that we have for shear reinforcement in ACI is 0.75 square root of F prime C, and that's floored at 50 over FV. FV is the yield strength of reinforcement. And so if we look here at this plot, we've got minimum web reinforcement on the y-axis and the concrete compressive strength on the x-axis. And so if I just plot this equation for 60 KSI steel, we have this line right here in ACI. And then AASHTO is 1 square root over FV, so it's a little bit higher. For non-slender beams in ACI, it's 0.25% in each direction, or deep beams. For AASHTO, it's 0.3% in each direction. And so you can see that line right here. And so the discrepancy would be the difference between this line and that line, right? So for regular reinforced concrete, 4,000 PSI concrete, we've got about 3 times more reinforcement required for a deep beam than what's required for a slender beam. So just to illustrate what are the implications of that, so if ACI says that a deep beam is anything where the load is closer to the face of the support, anything that's less than 2 times H, the deep beam would require 0.25% reinforcement in each direction. If you were slightly bigger than that, you wouldn't fall into that category. Most designers then would just design this as a slender beam, and you would only require 0.08% minimum in each direction. Real quick sort of overview. So slender beams, we were talking about the mechanism of shear transfer as VC plus VS. VS is the amount of steel required. Sometimes we can idealize this through a parallel core truss model. The parallel core truss model doesn't account for the contribution to shear from the concrete. And so if we look at this free body diagram right here, we say that the shear capacity of the beam, VC plus VS. VS is the amount of force carried in the stirrups. VC is everything else that from empirical tests. Another thing to point out, ACI, the angle of the strut is taken as a constant value of 45 degrees, and AASHTO, because that's based on the modified compression field theory, that would use a variable strut angle based on the strain in your bottom chord. The mechanism of shear transfer in a non-slender or a deep beam, the load would be carried from the point of application directly to the support, and the capacity of your beam would be a function of the capacity of the struts, the nodes, and the ties in this tied arch that I have right here, where we're just looking at the stress times the area of each one of those elements times some efficiency factors. And then one more piece of background, where do the minimum requirements come from? Well, in 1956, the minimum shear reinforcement that was required was taken as the amount of steel needed to resist the shear stress that causes diagonal cracking. It's also similar to how we derive our minimum flexural reinforcement as well. It's the amount of reinforcement needed to resist the flexural cracking. So that's 100 PSI, which these are a little bit older slides here. So 100 PSI is 2 square root F prime C. If F prime C is 2,500 PSI, which is the minimum value in ACI. So just kind of how like we say VC is equal to 2 roots. The amount of steel needed to resist the shear stress that caused diagonal cracking was also 2 times the square root of 2,500 PSI, which is the minimum concrete strength we can use. In 1969, according to McGregor and Hansen, that requirement was reduced to 50 PSI. So now we're allowing the concrete to carry half of that shear, so concrete will carry 1 square root F prime C, and then the steel will carry the other 1 root, or 50 psi, which is about half. So the requirements that we have for slender beams appear to be based on a strength requirement, right? They're based on making sure that our beam has enough strength, or it can meet our estimation of what the strength will be. For non-slender beams, in the commentary of the code, it'll say that the minimum reinforcement requirements are intended to control the width and propagation of incline cracks. And so for non-slender beams, then it appears that our requirements are based on a serviceability requirement, right? So we have 2 different criteria depending if we're a slender or a non-slender beam. And so for this study, we just decided to take a closer look at that and see, is that the case? To do that, we compiled these data sets right here. And so the first 4 are Reinix data sets. And then in order to get some more cracking data, I added in 2 data sets of my own as well. And so over here, you can kind of see the characteristics of the data in those data sets. The non-slender beams, we have 240 specimens, and the slender beams, we had 128 specimens. Okay, so one of the issues is that a lot of researchers don't actually collect crack data, okay? And so we have crack data for about 30-some of the non-slender specimens, but we didn't have any crack data for the slender specimens except for 2, these 2 right here. And so what we did was we just decided to predict the cracking response for 100 odd beams in the slender database. And in order to sort of verify our approach, we matched, well, how are our predictions lining up against the beams that we actually know what the cracks are, right? So for example, so what we're seeing here is in the black, this is the crack data reported by the researcher. And then in orange, that's the crack data that we predicted, and we used Evan Bentz's program for predicting the width of the diagonal shear crack. The percent V test, so that is the percent of the ultimate capacity of the test specimen. And so here you can see the comparison between the experimental crack width and then the predicted crack width. And the findings were basically that, well, for specimens whose shear is less than 70% of their ultimate capacity or their test capacity, the program was able, or we were able to predict cracks within plus or minus 40%. That aligned with a statement by Leonhardt that also pointed out that variation about plus or minus 40% is what you can expect for predicting crack widths. As it will turn out, you'll see the widths aren't as important necessarily as the trends in the crack data. Okay, so let's get into some results here. So the shear strength of slender beams, we're looking here at, these are the ACI predictions on the left and the AASHTO predictions on the right. On the y-axis, ECR stands for experimental to calculated ratio. So a value greater than 1 means that the experimental capacity was greater than prediction, right? So that's a conservative test. And then on the x-axis, we're plotting the shear reinforcement ratio, rho v, normalized by the yield strength of the stirrup reinforcement and normalized by the square root F prime C. We can see here from the results that the ACI limit and the AASHTO limit seem to be drawn about where the lower bound of the data trend is starting to dip down. There are a few other sort of outliers. The beams by Tan and Rosenbusch, those have a stirrup spacing that would exceed the ACI maximum. And the beam by Tanimura and Sato was compression controlled. And so I would say that these are likely failing at a lower value, not because of their shear reinforcement percent, but because of these other factors. The tests by Roller and Angelikos, these tests are actually the tests that led to this code provision, the 0.75 squared F prime C. And yeah. Okay, so we can do a similar plot for the shear strength of non-slender beams. And so for the non-slender beams, again, ECR, now we're on the x-axis. Because the reinforcement for non-slender beams is usually specified in each direction, we're plotting these versus the square root, or the square root sum of the squares of the vertical and horizontal reinforcement. So the square root of rho v squared plus rho h squared. A couple low points here for the non-slender beams. These are, two of them were compression controlled, one of them was in the transition. They also had a really high compressive strength of concrete, which can lead to inefficiencies sometimes with the strut and tie model. And so similar to the other one, I would say that these low values are not because necessarily of the reinforcement percentage, but they're due to other factors. There is two data points on top of one another right here that are kind of dipping a little bit more below the line with ACI. The same ones dip a little bit further when you use the AASHTO provisions. And that's about at 0.0017 on this graph, which works out to, if you divide by the square root of 2, it works out to about 0.12% in each direction in order to achieve the minimum, or in order to achieve a conservative estimate of strength. Onto the crack data now. So we have, this is the crack data for the slender beams, and this is the crack data for the non-slender beams on one slide. What I'm plotting here, so remember again, for the slender beams, we had to predict what the crack width is analytically. We said, well, what if our predictions were off by 40%? If cracks are 40% underestimated, and they're actually 40% larger, these gray data points sort of slide those down accordingly. The other things about this chart, so on the y-axis, this is the percent of v-test when the crack width is should be 0.016 inches. That decimal shouldn't be there. 0.016 inches, which is the serviceability limit, or it is a commonly used serviceability limit for cracks in concrete. The approximate service load of 33%, so that was derived in a paper I was part of, I'd say almost 10 years ago, by Bircher et al. If you look at load factors, strength reduction factors, and then the fact that test values on average are about 1.5, have an ECR, an experimental to capacity ratio of about 1.5. If you take all those factors into account, the serviceability limit on average is about 33% of your test value, right? So if your experiment, failed at 100 kips, then if you would have designed that beam for service, you would have designed it for 33 kips at service, roughly speaking. Okay, so that's kind of what's going on at this chart here. So for this data point, for example, the crack was 0.16 inches wide when the loading was about 35% or so of the test value. Okay. So anyhow, none of these data points fall below the 33% service limit line, but there was a slight downward trend, or there was a noticeable downward trend right where this kink is shown, and that works out to be about, long story short, about 0.2% reinforcement ratio in order to get those cracks at 0.016 inches. Recall for the non-slender, for the deep beams, we do have crack data for those, for 37 of those. And so if we plot the crack data for those 37 non-slender beams, now again, this is what is the percent shear when the crack width is at 0.016 inches. For those beams, we get about 0.0027, which if we're plotting the square root of rho v squared plus rho h squared, that works out to about a similar number, about 0.2% or 0.0019 reinforcement in each direction. So what does this all mean? In conclusion, the amount of web reinforcement that you would need in order to achieve minimum strength for your beam, for slender or non-slender beams, it's about 1% square root F prime C over FE, a little bit more for non-slender or deep beams, 0.12%. The amount of reinforcement that you need for serviceability performance, so that's we're calling that a crack with less than 0.016 inches, is about 0.2% for each slender and non-slender beams. And so that's it, and I'd like to take any questions you might have. Thanks.